enthalpy of formation is the enthalpy change associated with the formation of a substance from its component elements. For example, if we look at the formation of water from its components, hydrogen and oxygen, and the enthalpy changes associated with that, in other words, the bonds that have to break between the hydrogens and the oxygens, and the enthalpy change associated with the formation of those new bonds, that net change would be the enthalpy of formation for water. And since we're talking about an energy change, then the state of the components is really important. For example, the amount of energy it would take to turn water, boil water, and change it into steam is really relatively small compared to the amount of energy it would take to turn ice into steam, from a solid to a gas. Most enthalpies are tabulated at a standard state, its pure form at 1 atmosphere of pressure and 25 degrees Celsius. So when you see this, you know it's under standard state conditions. And if an element exists in more than one form under standard conditions, then the most stable form of the element would be used to determine the enthalpy of formation for the reaction. This is the formation reaction for ethanol. And since we see that we have a negative value for delta H formation for the reaction, then we know that this reaction must be exothermic. The stoichiometry of a formation reaction is always going to be written so that 1 mole of the desired product is going to be produced. So our units for delta H formation will always be in kilojoules per mole for 1 mole of product. And that's why you'll see fractions written as coefficients in this type of equation. This equation shows the combustion of 1 mole of propane gas. This enthalpy diagram depicts the enthalpy changes for that equation. We can see that the reaction occurs in 3 steps, where first of all the hydrocarbon has to decompose and the bonds in the oxygen molecules also need to be broken in order for the molecules and the atoms to rearrange themselves. In the second step, for the formation of the carbon dioxide, where the carbon and the oxygen bond together. And in that instance, since new bonds are being formed, energy is given off. And then in the third step, we have the formation of the water molecules. Again, a formation reaction where energy is being given off. Hess's law tells us that we can calculate the delta H for the reaction by adding up the delta H for the first, plus the delta H for the second, plus the delta H for the third step to get the delta H for the overall reaction. We can also calculate the change in enthalpy for a given process by using this equation, where essentially what we're looking at is the difference between the changes in enthalpy of the products minus the reactants. This sigma means the sum of, and N and M refer to number of moles. So if we wanted to calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide and water, this is the way that I would write the equation. I'm writing it as 1 mole of benzene, which is why I have a fraction here for the oxygen. So I can calculate the delta H of the reaction by using this equation. And the delta H formation of all of the species present in this reaction are listed in Appendix C of the textbook. So using our equation, the delta H for the reaction is going to be equal to the sum of the delta H of formation of the products minus the sum of the delta H of the reactants. So starting with the products in our equation here, we have 6 moles of carbon dioxide. So I'm going to need the delta H formation for the carbon dioxide, and since there are 6 moles of it, and my units are given in Appendix C in kilojoules per mole, I'm going to have to multiply that by that coefficient of 6. To that, I'm going to need the delta H formation for water, and since there are 3 moles of it, I'm going to have to multiply that by 3. Remember that delta H is an extensive property, so I've got to take into consideration the number of moles of all of my reactants and products. So once I've got the sum of that for my products, I'm going to have to subtract the delta H's of my reactants. And so I have my benzene, which is in its liquid form, and there's only 1 mole of it. And my other reactant is the oxygen, and the coefficient there is 15 halves. And then we'll have the sum of our reactants. Our next step is going to be to go to Appendix C and look up the values for the delta H formation of all of our reactants and products. Paying very close attention to the states of our products and reactants and making sure that we select the appropriate values from Appendix C. And so I have found that the delta H formation for gaseous carbon dioxide is negative 393.5 kilojoules. And for water in its liquid form, we have negative 285.8 kilojoules. And for the delta H formation of our liquid benzene, we have 49.0 kilojoules. And finally, the delta H formation of oxygen, which is a pure element. The delta H formation of any pure element is always going to be 0. And so once we have multiplied by our coefficients, gotten our sums, and subtracted our products minus our reactants, we get a value of a negative 3,267 kilojoules. And of course, that negative value for delta H tells us that it is an exothermic reaction, which is exactly what we would expect a combustion reaction to be.